Yeah.
Yeah, let's get started.
Yeah. Can we have all the panelists?
Hello.
Okay, yeah, I can.
Hey, Charles.
Okay, great. Let's get started. Yeah, I think wonderful talk. And so I guess maybe we'll first start from each panelist up to 3 minutes, talk about, say, maybe one important problem they think has made really big progress, right? And what are the next challenges? And then we'll go into panel discussion after. Yeah, so we can go with alphabetical order of first name. I guess Andy.
Hey, yeah. So I think that what we've been really good at least in 3D vision, is being able to train these awesome shape classifiers. And I feel like we could find ways in which we can leverage those in robotics much more. And I'm generally excited about because I think that as we start to think more about shape perception problem and its connection to interaction in the physical world, and I think that suddenly a lot of things start to naturally feel like they make more sense. For example, what makes a doorknob is not that it belongs to a category 26 out of 1,000 other categories, but that a doorknob is twistable and that it affords the embodied agent to move from one room to the next. And I think that this kind of ties into a body of work with origins in graphics in the 90s and early 2000s that explores ideas related to how shape informs functionality. And while that has typically been in the context of shape clustering with applications in video games, for example, I think that robotics is actually coming to a point where it can also benefit a lot from those ideas as well. So I think it's a good time for us as a research community to revisit those topics once again. And given that it has been a decade since then, I think it's due for a modern re-examination, and this time with deep nets and robots.
Cool. What will be the next challenge in this like applies, leveraging shapes? Yeah.
Yeah. So I think specifically for these neural nets, how do we condense the mapping from interactions to shapes, I think is open question. So that ties into representation learning and how do we precisely do that? And I was advocating for affordances in my talk, but I think there are other ways to do that.
Okay, great. Next, I guess Charles. Charles, can you hear? We kind of lost Charles. Oh, you're muted.
Oh, okay. Hi.
Yeah. Charles, yeah.
So hi everyone, this is Charles. I'm currently a research scientist at Waymo, so from the autonomous driving industry. So I want to share some challenge we currently face in autonomous driving, which definitely is a very large-scale robotics application. Also has a lot of things to do with 3D computer vision and perception. So I think it has been an industry for quite a long time. Like if from the research perspective, there is like autonomous driving research like 30 or 40 years ago, but then it really took off like after the DARPA challenge. We see the progress first happen in the mapping stage of the pipeline, where we have SLAM and localization technologies, which becomes quite mature nowadays. And then we see progress in perception, starting from the deep learning around 2013, then 3D deep learning and 3D detection and all those different architectures, which nowadays I think are already pretty strong. And then the interest of the community shifts more to behavior prediction. How do you do motion forecasting, which is like one step beyond just the perception. And then the more challenging problem is the planning, right, which doesn't have a well-defined loss. that's more open. But then even if you think of perception, it's not a solved problem yet. Right? We have defined those problems as classification, detection. We make good progress. But I think we are up to a stage where those simple metrics will not work well for our goal. So because perception in the end is still just a module of the system, right? But how do you know how to improve perception to improve the overall end-to-end system performance? It becomes very unclear if we just depend on the traditional academic metrics on like 3D average precision or classification accuracy. Because in many cases, what matters more is those long tail cases, which becomes the bottleneck of the whole system. So in terms of that, I think for perception, when you consider it, it's the interface to other modules and the way that we evaluate and iterate on these perception modules that needs more research and discussion. Because it quickly becomes non-trivial for you to judge whether it's a good perception system or not, or whether your newly designed model would improve the final training metrics. And we currently don't have enough research into that, I think, because usually for academia, we have well-defined data set and well-defined metrics, and people just try to kind of overfitting that metrics to become the first on the leaderboard. But that definitely have a gap to what the real industry cares about.
Great. Francisca, you want to go next?
Sure. Hi, I'm Francisca, and I'm a research scientist at Facebook AI Research. I guess in my research, I'm very concerned with on-robot learning. So I'm very interested in actually designing algorithms that work in the real world as we're, so that the robot can collect the data itself. And in that context, I see many challenges still open. Where I've seen a lot of progress recently, which I find exciting, is this, what I talked about is the learning from visual demonstrations from various angles, whether we learn policies directly from visual demonstrations or reward functions like I've presented work on. So that I find exciting, and I'm continuing to watch. I always care about sample efficiency, so that's why I kind of try to develop model-based algorithms that use a model to learn, for example, reward functions or policies. But of course, as I've also shown in my talk, learning these models is actually highly challenging. So how to represent these visual dynamics models, for example, such that they have a chance of generalizing, but also getting the right data that you need to learn the model, this is still a really wide open challenge. And this could be studied in simulation as well, of course. So yeah. And then safety is always a big issue with robots. As you're trying to learn in the real world, you need to optimize policies that you can try out and roll out, but you don't want to break the robot or the human or the environment. And we often don't worry about it in simulation, but in the real world, this becomes like a serious challenge. So yeah, I guess that's something I'm still waiting to see developed a bit further.
Okay, yeah, thanks, Francisca. How you want to go next?
Sure. So I would think that robotics research or embodied AI research have connected the opportunity for vision to connect with multiple other disciplines. For example, well, I completely with Andy that a very important aspect for robotics research is that for our computer vision today, we actually know how to perceive, kind of know at least how to perceive, right? We have a lot of network architectures, but do we really know what to perceive? But in order to enable interaction, enable like manipulation, navigation, there has to be like new representation emerge. This is a question for connecting vision with cognition. And also, okay, so for the good representations we learn from 3D, right, they should allow us to achieve better generalizability. When we talk about like manipulation learning, the generalizability challenge is actually very different from the kind of generalizability we're experiencing in the typical vision task. For example, like you could say in reinforcement learning, people talk about generalizability, but the generalizability is more like in an online learning sense. It's not really a cross-object generalizability. So there are certain kind of connections that robotics bring us to think about, for like extending the connection with machine learning and vision. And then there's the question about like the causality, right? Because manipulation or interactions brings in a temporal dimension. And then you could actually learn about the precondition, post-condition, and the causal reality between before and after execution of actions. This is a very important question to think about. And then there's a relation between like vision and graphics, right? So somehow we used to do graphics for realisticity, but today we might want to do graphics for like helping robots to learn. That involves not only the visual realisticity, but also the physical simulation realisticity. Many kind of questions robotics bring us. I mean, it helps us to connect vision with a lot broader AI disciplines. That's my opinion.
Okay, great. Yeah. Manolis, do you want to go next?
Yeah. My perspective may be slightly different because I guess it should have been obvious from my talk. On this spectrum of simulation evangelist to simulation skepticist, I'm very much a simulation evangelist. So I'm entirely coming from the perspective of simulation and what can that do for us in embodied AI. So that's where my perspective on progress and challenges will be coming from. In terms of progress, what has been really amazing to see is all this recent effort that, all this cool work that has been happening in building better, faster, more capable 3D simulation platforms that can, simulate all sorts of really cool, rich kinds of environments, including environments with interaction. Work like how presented with Sapien++, Robothor that Rusbe was talking about, the Habitat 2.0 work. It's really cool to see this activity. There's clearly a lot of effort being spent on this, and I'm convinced that in the coming years, 3D simulation will be increasingly playing an important role in embodied AI and of course in robotics research as well. Now, in terms of the challenges, I think despite all of this, there's a big danger, a huge danger when it comes to basing a body of research on simulation, right? There's this danger of that simulations are in some sense doomed to succeed. That's a famous quote. And that they have all these pitfalls and ways that they can be gamed, and it's not at all clear whether what you do in simulation is actually measuring real progress in the real world. So I think many interesting challenges lie there. Questions like what are the right kinds of approximations to take in a simulation, or right abstractions to make that will still allow our simulations to be predictive of some real scenario, to be useful in evaluating and ranking different methods, different agents, different AI for different tasks. These are, I think, very interesting questions, and I don't know that people have very good answers to these questions yet. So that's where I see the big challenges being finding the right abstractions, the right approximations, the right things to care about when it comes to simulation. So yeah, that's my perspective. I'll just leave it brief.
Yeah, thanks, Manolis. Rusbek, do you want to go next?
Okay, yeah, I talked about visual navigation and the issues associated with that. We have made a good progress in the past couple of years, but there's still a lot of exciting challenges ahead of us. So one thing was there are some challenges in training real robots. So in terms of the speed of training, so they're not as fast compared to simulation. There is there are generalization issues, reproducibility, and also safety. So simulation solves these problems to some extent, but at the expense of under modeling the physical world. So I agree 100% with Manolis that basically we should be very careful when what type of abstractions we are using, what type of sensors we are using, what type of problems are we are using. So any assumption that we have in simulation should be also valid in the real world, because we have access to a lot more data in simulation, but those types of data might not be available in real world easily. Or so when we define problems, when we propose methods, so we need to be careful and make sure that the assumptions that we have made are also applicable in the real world.
Okay, great. Yeah, thanks a lot for the great introduction. I think that sets the stage for some of the focus questions I want to ask the panelists, and then afterwards we're going to open the question to the audience. So one of the questions I think some talks already covered is robot manipulation, right? So we have all these cool machine learning algorithm that developed, let's say, imitation learning, reinforcement learning, right? And then, so I think we made a lot of progress. So even is able to do something even on like, these non-rigid bodies, right? And Andy covered about, leveraging shape. So I want to see that what are the gaps, right? Given the progress, like what are the gaps, right? That, in terms of machine learning algorithm, right? So that we can, that's preventing us from making further progress. And then what we think would be a good direction, right, to close these gaps.
Are we going in alphabetical order or jumping?
I think we just open. So anyone, maybe you want to go first since you went last.
Yeah, sure. Okay.
Mm-hmm.
So for most of the problems in embodied AI, we usually use, for example, imitation learning, or we use reinforcement learning. And for example, imitation learning sometimes it's not really possible in some scenarios. Like for example, for robot manipulation, you're dealing with a 3D continuous space. Like finding the optimal path in that space is not trivial. So that so imitation learning might not be really possible for some applications. RL has its own issues. It requires millions of iterations of training to learn a simple task. So people have used a combination of the two and so on, but still not very successful. So I think we need some new paradigms for embodied AI. So we are so the learning methods that we need should be kind of different. So one reason is that the data is different in embodied AI. For example, there is no clear supervision. So we might only know the goal, the final goal. We don't know how to reach that goal. So there is no cleanup for our data. For example, sometimes so we receive a large amount of data. Only part of it, a small part of it, is relevant to the task. So, and that relevant part might be noisy. So, another thing that we need to consider is training and testing should happen simultaneously. So, it's kind of different from traditional machine learning that we train a model, we freeze that model, and we test it at test time. So we should be able to train at test time. We should be able to adapt our models at test time. And also from the perspective of tasks that we should, in embodied AI, we are dealing with interactive tasks, which are very different from passive tasks that we typically address in computer vision. So the data, so we receive a stream of data and streams of data, and also we encounter new situations in like in every second. So our learning algorithm should be able to deal with these rapid changes in data. So an annotation that's accurate at this second might not be accurate like in like 10 seconds later. So our model should be, or our learning algorithm should handle these scenarios. And I think we need some change in the embodied AI domain in terms of learning algorithms.
So what would think those would be, what would be a good direction?
I'm not, yeah, I'm not quite sure. I mean, if I knew how to do that,
okay,
I would do that already. But there is something, I don't know. It might be like some we might need like some form of pre-training, like some learning skills and these types of things, or it can be more on the theoretical side, like some probably we need some innovations there that so we can elegantly update the model, like as opposed to like update the entire model that just for a specific instance of data. So these types of things.
Okay, great. Anyone else want to chime in on this question?
Yeah, kind of connecting to sort of model-related challenges that Rusby was talking about. I think manipulation, a lot of it is really about handling contact dynamics. Like, contact dynamics are typically represented by discontinuities, both at the physics level, at the state level, as well as the observation level. And so it's interesting, one of the spotlight talks earlier today from Athanasios was showing a few haptic signals with the haptic gloves, and very clearly you can see that the data that you get when it comes to manipulating objects is really discontinuous. And so I think what we're kind of still working on in robotics today is finding the right models that can represent these discontinuities and then map them to mode changes in robot behaviors. So for example, the actions that the robot would take before it comes in contact with an object may be different from the actions that it would take afterwards. And what is the best kind of machinery that we can do to model these discontinuities? I'm not sure. All I do know is that end-to-end deep nets trained to explicitly regress actions from states, they tend to perform poorly on handling these types of discontinuities, because this is partly because during training, you kind of have to be lucky with one of your activations actually landing and being able to capture that nonlinearity perfectly. Otherwise, the back propagation gradients might be unstable, and this is likely because the first order derivatives of discontinuity can tend towards infinity. So I think finding the right machinery to be able to tackle the manipulation problem, I think, is still an open research question, and I think it's an interesting one.
Yeah, great. Thanks,
Andy. I also want to comment a little bit over this problem. I feel that manipulation is actually a very wide spectrum of problems. Right? There are some simple ones like pick and place. We could say this is the manipulation, especially pick and place like rigid objects. There are also the very challenging ones like to playing with ropes or like to playing with chopsticks. Right? So some it's very hard to model. Some are much easier to model in terms of the law, right? The physics law. And for the very challenging ones, it's even some of the manipulation skills are even not quite possible to be only achieved through vision. As Eddie said, like haptics, right? To get the feedback from the force, this is important. And I also think that in manipulation research, there's a very important aspect people didn't mention much, which is, okay, basically manipulation are usually closed loop control problems. Are we solving the optimization problem, but we want to interact and solve the current, the manipulation of the current object or we're learning kind of a generalizable strategy that will generalize to very much like the unseen cases. Like especially when you are manipulating certain kind of soft objects, right? There might be very large amount of unseen cases, whereas capturing the data is hard. Like as I said, if you want to capture haptics, the sensor devices are not even so ready. So I think, maybe there should be a good order of studying those manipulation problems, starting from certain simple ones and help us to build network architectures and then gradually move to the very challenging ones. That's some opinion I have.
Yeah, thanks, Hao. Those are great points. Anyone else on this question? Francisca, you talked about a bunch of machine learning algorithm what you develop, right? So what the gaps you see? Yeah.
I definitely think that sample efficiency is something that we need to look at more. And I see this because I do try to work on the real robot as much as possible. And then, the real world, the real time is the real time. We can't speed it up like we can in simulation. What I also have been thinking about a lot recently is learned state representations that generalize. This is something I noticed specifically as we were working on the model-based inverse reinforcement learning, where we were trying this model in the learned latent space, and that latent space matters a lot for actually being able to learn a predictive model in it. So how can we learn state representations from multimodal sensors that generalize across tasks? I think this is a huge open challenge, but so important. So that's something that comes to mind right now.
Okay, great. Yeah, I think generalization, I think several panelists have already mentioned that. Do we need some do we have some kind of promising approaches? Like I guess Hao mentioned about causal approaches. There's a bunch of like machine learning that does causal inference, right? The structured causal model, where you have other ladders where you can you have do interventions, right? You can also do counterfactual stuff, right? Do we need those to close the gap? Is that a nice framework to think about generalization? Yeah.
Yeah, I'll share a little bit of my thought over this problem. So first of all, you see that in a challenge that I'm promoting, we're talking about the manipulation scales. The reason for us to actually separate scales out of manipulation sequences, like the manipulation can be very complicated. It involves a lot of action primitives. And perhaps understanding this long sequence, the causality perspective is very helpful. On the other hand, at the scale learning problem, meaning that you just want to master kind of like an action primitive. I personally think that it's kind of like the recognition problem in vision, that the causality plays less role than learning good distributed recognition. It's kind of my feeling, but this might not be correct. Yeah. But it also implies that when we talk about like composing the primitives into long-term plans, causality could be very important.
Yeah, that's a good point. So yeah, learning primitive could be learned without causality. You're right. So then if you want to compose to achieve a task that needs these primitives to work in a causal way, right? Instead of just learning the spurious correlation. Yeah.
I'm happy to share one thought I have about learning. I think
Yes,
it's about lifelong learning or continual learning. I guess people in the panelists, they might be really interested in. But I do not see currently we really have a system or a robot that can really lifelong learn, right? I think the concept is great, but how can we achieve this? How can we have a robot that really continuously improve itself day by day and eventually become better and better? We may need to build infrastructure, right? How do you store all the data? How do you learn from all this daily data? It's gonna be massive data. We need an algorithm or learning algorithm to really achieve this lifelong learning.
So you have any like insights on like how can we achieve this? It has been like a long time challenge in machine learning, right? So in the robotics domain, how can we really continuously learn? Right?
I have some thoughts on this. I would say the robotics community has been thinking about lifelong learning for a long time as well. And I don't think it's one algorithm that we can develop that does lifelong learning. I think it's a mindset more than an algorithm. And so to me, the mindset that the change that needs to happen is to think about not pre-collecting all the data that you think you might need and then trying to learn, but instead of like thinking about how can you generate the data that you need to learn the next task, and then how can you generate more data with what you've already learned so that you can increase the complexity of the things that you can learn. And so I think if people start thinking more about this, that you can't pre-collect everything that you need to learn, then you start thinking about lifelong learning already. That's my opinion.
Okay, and
Can also
go ahead.
comment on that.
Yeah, go ahead.
So one issue is that continual learning is still in its infancy. Like people usually test on a small data set, on limited data sets. And on the other hand, also robotics and embodied AI is very hard. So these are two things that are hard to do, and combining them, it makes things even harder. So I think that's why we have not seen a lot of work in this domain that works robustly and with high accuracy. So there are issues on both sides, on the continual learning side and on robotics and embodied AI side. So that makes it difficult to combine.
Yep. Great. Anyone want to chime in on this before we move to the next question?
Maybe I can say a bit. I feel that like the important part is to build a curriculum, right? I don't know, maybe certain kind of curriculum, even for humans. We grow up with certain genetically coded curriculums. And when we're very young, we're interested in certain kind of phenomena. When we grow older, our interest naturally shifts. This kind of a genetic coded, interest change. It's kind of also like curiosity is driving our interest in developing this kind of lifelong learning ability. I guess there are certain kind of research in this line, the machine learning community, especially in the reinforcement learning community. And perhaps you can take a look, but as Jessica said, this kind of also and Roosevelt said, this kind of also an infant, kind of an area of this infant stage. So using machine learning to generate interest, generate curiosity, to develop a curriculum and maintain the continual learning. This perhaps is a very important if you want to really push the manipulation research. As I said, I also feel it's relevant to the claim that manipulation skills has a spectrum from simple to hard.
Okay, great. Let's move on to the next question. So what is the right interface between 3D perception and planning and control? I think traditionally in robotics or in like, for example, self-driving, right? We kind of decompose it. We do perception, we got the objects, we got their kind of, we have the object state, right? And then we feed it, into the prediction and planning system, right? So is a very rigid interface, and then imitation learning RL has been really sort of doing this end-to-end, right? Like, image pixel in, and then you control command out, right? So I think there've been a lot of work also, like Francisca mentioned, like instead of this fully end-to-end, you can learn some latent space, right? Maybe it's more structured latent space, and or there might be kind of a combination, right? So where it's end-to-end, but you kind of you still like at some of the components you could have these auxiliary tasks, right, that learn perception, but you don't give the the kind of object boxes to your planning control system, right? So trying to see that what do you guys think about the right API? Yeah.
This may be a bit of a facetious response, and maybe betrays again my my biases as a computer graphics person, coming very much from the from that perspective. But hearing this question about what's the right interface between perception and planning/control, I can't help but think, what's an existence proof of something that we have done that involves both perceiving a world, creating it, and then also acting in it. And I think of 3D computer graphics engines, computer games. And then I think of how, people on one side, people are responsible for, maybe through their perception of some real place or imagined place, creating, a world, right, in a computer graphics engine. And then on the other side, somebody is then responsible for acting in it. For actually through some mode of control, actually interacting with that world, changing its state and so forth. And so again, this is a bit of a facetious response. It's not very deeply thought out, but I'm wondering, if we standardize, say, on an API of a video game engine editor and said, okay, all perception must feed into this API and create a video game world. And then on the other side, all planning and control must, actually interact with this video game engine API and drive, all the, characters and vehicles and things like that in this game engine. Would that be an interesting experiment, perhaps?
It sounds like an interesting experiment. I guess my question would be, like, my intuition tells me that the state representations that are important or necessary to have depends on the embodiment of the robot. So what kind of particular capabilities they have, what kind of gripper, what kind of arm, and whole body. And I think that's where this experiment then breaks, if I understood what you're saying. Now, this is an hypothesis. I can't prove it, but that's what I would respond, basically.
Okay, great. Manolis, you want to respond?
Yeah, just.
Oh, I don't have a good response. As I said, this was like a half-baked idea that I wanted to put out there for people to engage with.
Okay, Rusbek, yeah, go ahead.
Yeah, I don't have a response for Manolis, but going back to the original question. So there's a spectrum. So one is like being completely implicit and learn everything end to end, and the other end of a spectrum is basically making everything explicit objects, explicit map, and so on and so forth. So the issue is being completely implicit is very very difficult, and it's kind of unrealistic to expect the networks to learn all this without any supervision. On the other hand, the other end of the spectrum requires a lot of supervision. So you have to provide supervision for objects. You have to provide supervision for their state and so on. So I mean, ideally we should solve everything end to end, but given the state of the field, I think we are closer on to the more explicit side, and maybe for now we can we can use this explicit information and gradually relax this information so we can approach the other end of the spectrum and learn everything end to end.
Great.
Yeah, just want to share
Oh,
some
go
of
ahead.
my thoughts. I think it's also related to what Manolis has said in the game engine thing. I think an interesting thing to notice that actually a system like AlphaStar has succeeded in a very end-to-end fashion. If you consider their system, the input is your raw sensor data, like the images of the game. And then the output is the actions of multiple agents, actually. And the system worked really well, beating like top human players. But such design, I don't think it generalizes well to like a real robotic system like in autonomous driving. I think that's a very deep question to think about. Like, I think one aspect is that the uncertainty from real sensor data really exhibits a very significant challenge to have such an end-to-end system. Such that people would design those modular modules like, then that comes the question where you have perception, you have behavior prediction, and you have planning. But if you consider the AlphaStar, there's no such three systems. There's only one neural network from input data to the planning, right? And then I think rather answering the question like what's the best APIs, the real thing maybe we want to pursue is a simulating environment or mechanism that we can quickly verify our system design, right? To verify whether this interface is a good one, effective one, or whether it's an inefficient one, maybe because you lose information in that interface, or maybe you put too much complexity in one module. But I think we don't have currently very good such mechanism to verify our designs. Many things are still based on empirical like study and charge and like hand manually designed interfaces. And simulation is definitely one of the very important directions to automate all those design verification.
Okay. Anyone else has any thoughts on this question?
Maybe I have a comment about this interface or abstraction, and it's more of a comment, I guess, somewhere in between the end-to-end and the complete explicit. And even just a comment on the design of end-to-end networks, in the sense that usually when people design end-to-end networks, they usually don't just plop down or say a fully connected network and say, go. They usually design modules which may be differentiable throughout, but conceptually they may have a module that's like doing some perception, and then some other module that's like taking the perceived representation, and maybe the perception module is trying to say, oh, you know, this is a table, this is a chair, you know, object detection. And then they have something else that's like a planning module that's like saying, okay, now that you detected these things, what am I gonna do with them? And then maybe they'll hook up everything end to end and train it. I guess my comment here is that I do think that, you know, it is, as Elizabeth was saying, that it's not, it is a spectrum, and I think it's useful to think about these useful abstractions that we people have. And even if we design networks that are trained end to end, it doesn't mean that these abstractions or interfaces doesn't exist.
Yeah, that's a good point. Yeah. So yeah, even if end-to-end is, you want to be a modular system. Yeah. So yeah, let's move to the next question. So after this question, we're open up to the audience. So those in the audience, please feel free to type in your question, or you can just ask. So the next question is, in the context of this workshop, right, 3D vision and robotics, what are the underexplored areas of research? And then, for example, one may be like few shot or zero shot generalization, right? For example, that at least in a lot of the real world situations, for example, in pickup and packing in warehouses, right? So a lot of cases, you can't collect training data for every object, right? So a lot of them, you probably just see it once, right? So you have to know how to, pick up and pack, right? So you just have the question and see what are the panelists think, what are the underexplored area that's really important where we can make significant progress.
Yeah, so maybe I can share one thing first.
Yeah, go ahead.
I think for a long time that we are, as a community, we are working on predefined problems. Given this data set, improves the classification accuracy. Given that data set, improves the average precision. And then this is a very effective way for the community to work together with a shared standard. But however, when we consider a larger system, like in robotics, for manipulation, or even for augmented reality or for autonomous driving, perception is just the intermediate output, right? Just using those standard metrics to evaluate them can lead us somewhere, but then the progression stops after a certain period, right? People started to overfitting to manipulate the data set and the metrics. I think it worth more research to study how perception improvement results in final system improvement under some defined task, robotics tasks. I think a difficulty that why people don't do such research is there's not many platforms that support them to do this research. They cannot build an autonomous driving car to do this, right? They cannot build a whole robotic system to do this. So I think any public release of such environment will be very beneficial. I think there are already something, right? Like the CPNs or even the Facebook has those data sets released. I think this will be a trend.
Yeah, thanks, Charles. That's a good point. Anybody else? Maybe how you see, like, what is the gap between what you have and really sort of, we want to move out of the paradigm of just predefined task, right? So I think you built this Cyprian++. I think that's a very good initial step. What's your plan? What are the next set of steps, right, that can really move to the direction where Charles has been talking about, really sort of having these environments really impact the downstream task, right? Genuine improvement for downstream tasks, right? Rather than have a static data set, just at some point we stopped, right, the progress. Yeah.
Okay, thank you. Maybe I could first say a bit from a perspective of our community culture. Okay. Well, I started work on computer vision around 2016, 17, I think. Sorry, 2006 and 7, I think. Yeah, so I think at that time, computer vision is like it's like people are interested in vision. But I kind of feel that the community is gradually becoming only interested in architecture, either designing architecture or like searching architecture recently. Maybe this is also a consequence of deep neural network sweeps the community. But still, I want to say, as Charles said, I mean, it's important to think about like what are the problems to solve, not only how to solve the problem. So I hope that the community will leave more space to submissions that will explore this problem. Maybe they do not look so much mature at submission stage, but there really is a good space to explore. This is one thing. So I kind of feel that the community is not so friendly to many papers that are exploring how to define the new problems. I actually feel it's not only that someone defines the problem and people come to solve. I mean, it's better that there's kind of a more systematical way of creating or parameterizing the space of tasks. Yeah, so one of the Sapien manipulation challenge was to scratch the surface along this problem, which I feel that our efforts is still kind of very basic. So yeah, that's the reason that why we try to set up like the manipulation scale challenge. But I think maybe Ruthbeck, they have good idea of like setting up, I don't know, like the long horizon planning challenges. So there would be certain new perception problems that will emerge in either learning the manipulation scales or like learning the long horizon manipulation accomplishment, and also like for Andy's work for like the affordance perspective. They are all very good problems. And also there's a line of problem that's relevant to like what kind of role paths play. And in fact, it's even relevant to how paths are defined in a framework of manipulation. I think they are also very important, right? Yeah, so I recently do see certain kind of work that study the problem of the emergence of path decomposition for objects from like manipulation or I don't know, some kind of video data. Yeah, they're kind of good problems. Okay.
Great. Yeah, anybody else wanna?
Yeah. Oh,
Yeah,
go ahead, Andy.
okay. So yeah, on the topic of kind of evaluating manipulation, I think that we often try to compare with human performance for many tasks. And I think that it's kind of a unfair comparison because we have like 30,000 nerve endings in each hand, and we're kind of we basically have an unfair advantage. And I think this is interesting because sort of what I was talking about before about haptics, I think that we should start looking a little bit more at some of the other sensing modalities as well. Having tactile and force torque data, because as humans, I think they've been a driving part for what helps us build these 3D representations of the physical world, especially ever since we are children playing with toys. That's what we're doing with our hands. We're getting in there and really feeling the object. And so I think that an underexplored area that I feel like actually belongs in 3D vision is finding ways in which we can process some of the other sensing modalities like tactile or force torque or even sound, and bring them into this joint 3D representation that we can then enable policy learning downstream. So I think I'm particularly excited about that. And I think it's underexplored.
Yeah. Ruthbeck?
Yeah, I wanted to talk about like few specific problems that are kind of underexplored. I mean, they have been explored before, but they've not received much attention. So one thing is basically echoing what Charles said. So we need to be able to learn in dynamic environments. So we should kind of move away from fixed data sets. So fixed data sets are good. I'm not saying that they are bad. They're good because we can easily measure our progress. But the mindset should be kind of changed. So we should be able to handle dynamic environments, and we should be able to handle the streams of data, like and these types of things. Another problem that I'm interested in is predicting physical properties of objects and common sense in general by observation and by interacting with the surrounding environment. That's one thing that people have worked in this domain for some time, but it has not received like much attention from the community. Another thing is predicting the future state of the environment. For example, we should be able to learn how our actions, I mean, by our, I mean the agent actions, affect the environment, like how objects move, how scenes change. For example, if I do this particular action, what is the consequence of that action? So that we need to be able to model the consequence of actions. And also another thing that's kind of missing in I mean, not missing, but not receive much attention is memory. So we need to know like how we need to learn about our memorize our environment. We need to memorize the previous things that we have done before in that environment. But we have a lot of work, for example, in 3D reconstruction, SLAM, and those types of things. But if it's kind of immature yet. That, for example, if you make a change in the scene, how we want to model that that change, and we should be able to handle dynamic environments much better than before. So these are some random ideas that I was thinking that are kind of underexplored in our community.
Okay, great. Anybody else on the panelist? I think now we can open up to the audience. Yeah. So the audience, if you can just directly ask a question if you have a question. Yeah.
I think there's a question from Xun Da.
Yeah, we can just start from that question. Yeah.
So he's well, they're asking what's the biggest gap, sim versus real, in the field of simulated LiDAR point cloud generation? How far are we from requiring 10 times less real world data when real plus sim data is used? Okay, who is a LiDAR expert?
So this is a question for Charles. Yeah.
Okay, yeah, this is an interesting question. So I think there are several aspects in terms of simulation for LiDAR data. Like first, you need to simulate the kind of the pattern of the kind of distribution of objects, right, where objects should be, right? That's one thing. And then you need to simulate the physical signals, right? When you have this LiDAR, what's the return, the range image, the intensity, etc. Then you may need to have a material and assets of those objects. And then also you want to simulate the environment conditions. Maybe there's a raining weather, it's a snow, there's a fog. So it's actually a pretty complex problem. You need to do those three things right in order for the model to be useful and generalize to real environments. So I think this is still very active research direction. And then I think when you consider how can we reduce the data by 10 times if we use simulated data, then that's raised to the higher question behind it. Why do we want to simulate LiDAR point cloud? I think mostly it's for end-to-end kind of closed-loop evaluation of the system. So we can get uncertainties from perception, which we will know how this will affect the downstream behavior prediction and planning algorithms. Then if we understand this, then we understand that what matters for the final performance of the planner. Then maybe those are the mostly the hard long tail cases. Then that comes the question, how can you simulate those long tail, very infrequent cases? That adds another level of complexity to the whole simulation problem. I don't have an answer for you, but hopefully I have shown you why this is still a work in progress and some of the challenges overall.
Yeah, thanks, Charles. Brent, you want to ask your question?
Yeah, so I guess first, I think this is a great workshop, and being someone that went kind of from robotics to computer vision, I think this is all very great, and I love this panel and the speakers. And one thing I'm trying to do is just like come up with a way to kind of tie this together. You guys are talking a lot about like lifelong learning and this idea. And I think this is kind of underappreciated in computer vision, where if you're a robot, you can interact with the environment, you can generate new signals. So why don't we leverage that more? And this static data set type thinking really doesn't match that paradigm. And if I think about work like tossing bot, you know, I have no doubt that once we set up this problem and we have a bunch of objects, we could learn with enough experience to toss like a new object. One thing I'm wondering is, do the panelists have any ideas though on how a robot could learn like a new task? So I liked Francisca's work where she would have like a human demonstration to maybe try to speed up this process. But is there any way that we could have it where you would have like a human demonstrate this process? It would be someone putting these objects in a bin and the robot would try to imagine new ways of completing this task. Is there a way that the robot could learn to be tossing bot after seeing the human example of placing the object? And maybe to tie it in with a lot more of the simulation-based panelists, would it be possible for a robot to be learning from a human demonstration, but use simulation as a way to explore new paradigms of achieving a task without the risk of breaking things as it's trying to throw it into a cup, you know, in the real world, and then try to explore this in the real world? Is there any way we could use kind of human demonstration and exploration and simulation to learn new tasks, not just how to perform one task with new objects or in a new scene, but actually try something new?
Yeah. Who wants to take the question? So Andy, you want to go first, since it's mentioning like the scenarios that you talked about in your talk.
Yeah, I think kind of one of the biggest challenges, I think, as you sort of mentioned, we're in this setting where we're creating these tasks, these bespoke tasks, and we're kind of manually engineering them in ways that allow us to fit our machine learning models essentially and have this training and testing paradigm. Totally agree with that. And I think that to move away from that, at least specific to the idea of how can we scale up task generation and simulation, I think one potential way could be thinking of more about how did we put together these generative systems in graphics, for example, that are capable of generating these environments on the fly. And I feel like that idea could be something that's powerful in the sense that maybe something is generatively creating these tasks for a robot to be able to see new scenarios all the time. And then eventually using that as some form of retraining for a real robot system. So at least that's, I'm just spitballing right now. I think that there could be something interesting there for sure.
Okay, great. Yeah, thanks, Andy. Anybody else want to answer?
I just have a quick comment. I want to say that there is a big barrier here. So the action space of humans are very different from the action space of robots. For example, we have 5 fingers. Our joints move very differently from a commercial robot. So that's mapping this action space to the other action space, I think is quite challenging. So even we observe videos of performing the task. If somebody teaches the robot how to do it, still the action space is different, and mapping between the action spaces, finding that mapping is not as straightforward. It requires it's a challenging task.
Yeah, that's a great point.
Maybe I can also comment a little bit. First of all, I mean, if you're interested in the literature in the machine learning community, there's a field of like meta learning that focused on adapting the learned skills to new tasks, and also like the one-shot imitation learning or few-shot imitation learning. It really focuses on the question: if you have a new task, are you able to imitate based upon very few observations? On the other hand, although these fields are there and there are papers and some of like the progress, I personally feel a very important question is if you want to enable this kind of like a fast learning of new tasks, then you have to reuse certain components. And what are the reusable components? And that refers to one, the question we just asked, what is the correct interface? And the second, like you talk about like manipulation, what are the skills? There are all these questions that needs to be answered before we can really expect a low sample complexity, curriculum learning robot would work in our humans physical space.
Great. Anybody else want to chime in?
I just wanted to say I really liked Brent's question and all the points he touched on. I agree on actually everything that was said. And some of the additional thoughts I have is that the reason why I'm kind of excited about the model-based learning from visual demonstrations is that the robot learns the model of its embodiment and how its embodiment changes, like the visual predictions and what it actually then perceives, right? And so you can sort of detach the embodiment of the demonstrator from the embodiment of the robot that tries to mimic what is seen, and that is actually important in this context of different action spaces, different embodiments, and so on. So that's one point I wanted to kind of make. And then to me, this question of lifelong learning on fixed data sets versus in robotics, I think not only should we be using the capability of the robot to interact with the real world, I think it's actually part of the question of lifelong learning, because you need to be able to generate the data to learn from as a robot. You will not get this fixed data set. So it's not just a feature, it's actually part of the question, in my opinion.
Okay, yeah, thanks, Francisca. We have a question in chat. Anuj, you want to just ask? You're here, or you want me to read it out?
Yeah, I'm here.
Yeah, go ahead.
So, I mean, we have a lot of presentations about object interactions, robot object interactions, etc. So this is a question that always comes to my mind. We have a lot of literature and a lot of recent works on hand grasps and robotic grasps. So what is our next step in that research direction, as in what hasn't been achieved yet?
Okay, who wants to take the question?
I could try to jump start at it. I think when we think about a lot of the latest grasping work, I think it's incredibly exciting to see that we're capable of handling kind of more and more variety and diversity in environments. And I think that if we kind of take a step back and look at the types of objects that we're manipulating, I think that oftentimes they're rigid, and if they're deformable, they're kind of like deformably rigid. I think what's interesting is to see if we can expand on the diversity even more. So looking at the interaction between the end effector and the objects, and then going from deformables to potentially even fluids, and granular media, and how we can potentially interact with those sorts of objects. So that's the first thing that I have. And at least I think that is kind of the next step, which is how do we grasp the deformables, and how do we interact with those sorts of things where there's an infinite continuum of states that the entity could potentially hold. The other side of it is that not only in terms of the objects there's diversity, but then we can also think about end effectors having diversity as well. So in manufacturing, there's lots of really cool end effectors. Like you can, I think suction is just freaking awesome. It works for a lot of different objects, and the cool part about suction is that you can control air in various different ways. You can also use the same tube to be able to blow things too. And so the question in my mind is that, could we look more at how to leverage the dynamics of these end effectors more in better manipulating objects in ways that maybe we even humans could not perform? And I think that's particularly exciting. So just looking at the diversity of both sides of the problem, objects and end effector.
Thank you. Thank you very much.
Great. Any other panelists want to chime in?
I can mention one direction. I think the grasping field focuses more on the grasp gripper pose, but after generating the gripper pose, we also need to have a motion plan to reach that pose. I think how to jointly have the arm motion and the gripper pose inferred together could be a very good direction in the future.
Yeah, especially when the environment habit is cluttering. I mean, the planning it's not easy, right? You not only need to propose the graph, you know, to think about how to execute it.
Great. Anybody else? Okay, I think we're already over time, so I think we're gonna end the panel. Yeah, thanks a lot for the panelists for the great discussion.
Thank you.
Yeah. Andrew, you want to give the closing remark?
Oh, yeah. Thank you. I would like to this will be just really super short. I would like to just thank everybody for coming, the audience for attending our workshop, and the panelists and speakers for giving such awesome talks and having such an awesome, panel session. I think it was very, very interesting, at least for me, and hopefully for everybody as well. And just thank everybody, and also thank Erran for running the panel, and thank you for doing a great job, like introducing everybody and asking questions. And I will thank UK too, except he's not here. But yeah.
Thanks, Andrew, as well.
Thank you.
Yeah, thanks very much.
Yeah, I hope everybody enjoys the rest of the day and the rest of CVPR. Yeah.
Yeah.
Thank you.
Thanks, everybody.
Thank you.